Hey, welcome back to another part of the series where we'll be designing a Slapdown intake. So far what we've done, just as a quick recap, is we've drawn up our master sketch, which shows us where the points of our rollers are going to be. This one's not really in the right spot because I moved at the end of the last part, but that's okay. And we also determine where our pivot point is going to be and where our rollers are going to sit when the intake is stowed. Then what we did was we drew out the intake plate, the plate that comes out of the robot. Today what we'll be doing is we'll be drawing up the plates that hold the motor that drives the pivot, this guy here, or this guy here. So let's get right into it. The first thing that I probably want to do is I want to draw out my drive base, right? Because this intake plates are going to be driven by a pivot, which is driven by a motor and a gearbox that are mounted onto a drive base. Now ideally what you would have is drive base CAD, where you could like use this derived thing and just throw it right into your part studio, but I don't have that. I think if you were building a robot in the season, you would have that, but I don't. And since we're doing this for the videos, I'm not going to go and make a drive base. I mean, I could, it won't take too long, but I'll just show you another method now, which is just the same. So what I'll do is I'm going to start a sketch. I'm going to just draw up a drive base in this part studio. So I'm going to start a sketch on the top face, right? And what I have here, no, not that one. What I have here is, you know, where the plate is relative to the rest of my drive base, and I can use this sketch to kind of base everything else off. So, give me a sec. Okay. So I kind of want to like draw out, yeah, what is it actually going to look like? Right? So, let me think about this. So what I would probably want is, I'll go normal. Oh, I can't see anything now. Struggles. I'll go normal. I'll go almost normal. And I'm going to just draw a big rectangle like this. And this rectangle, it needs to pass through that point there. It's going to be like the front rail. So to make it pass through that point, I'm going to use the coincident constraint, and I'm going to do line to a dot. So now that's constrained. Now my dry base rail is going to be rectangular hollow section. RHS aluminium. It's going to be like this. Right. It's going to be 50 by 25. Yep. 50 by 25 by 3 is millimeters the thickness, but I don't really care about that because, yeah, you'll see why later. No, sorry, it's because I'm not really interfacing with the thickness as much, so I'm not going to bother to CAD it. And then, I don't know, this one doesn't really matter because I'll play with the sketch later. This is the distance from the edge of the rail to the plate, to that plate there. And I want to draw the rest of the rails, so draw another rectangle, do that, and this one's also going to be 25, so I'll make this equal this, and now obviously I need a rail here, like every FRC robot has, so instead of drawing another rectangle, I'm just going to draw a center line at that midpoint. You can see if you hover over it, it gives you the midpoint. And sorry, I'll go normal. I'm going to make that a vertical line construction. So I click Q there. Actually, I'm back. Sorry about that. I just wanted to install a program that lets me log my key presses. Like it shows you my key presses, like that. So what I was trying to do is make a mirror line. Yep. So now that I've done that, I can go mirror. Select the mirror line. Click on this guy, select entities to be mirrored. 1, 2, 3. Now usually we don't really like this blue stuff in our sketch. I'm just going to constrain as much as I need to. I don't care as much about this blue because it's just the length of it. I'll make it sufficiently long, I guess. Say 400 should be enough. This one I'm probably gonna do 750, but you know, it really depends robot to robot. Like your frame size can change. Remember that we're drawing the frame out here. So once you've done that, you can extrude that guy out. Remember that we said we're doing 25 by 50, so this guy is going to be 50. Yep. Oh wait, no. I want to do a starting offset because, you know, we said that the bumpers we're going to figure out, and so is the frame. So 20. Oh shit. My bad. This one's supposed to be 20. Now remember that. Just keep in mind that your bumpers are probably not going to be this high. I mean, your frame can be whatever height. It really depends on like where your wheels are, for example, and how you've mounted your frame. But your bumpers should probably be as low as possible, and that gives you several advantages. One of them is being a lower center of gravity. If you lower your bumpers, it means that your you know, bumpers weigh something. So if you lower them, you get a lower center of gravity. You can accelerate faster because you won't tip if you accelerate quickly. And also, another benefit is it's harder for game pieces, you know, objects in the field to get stuck under your robot. It's harder for them to go under your robot, so it's always best to lower your bumpers. Yeah, okay. Now we'll have to draw the swerve modules in the corners. So how do we know the dimensions of a swerve module? I'm going to create a new part studio, and I'm going to insert an MK4i. This is the swerve module that we have. MK CAD. Okay, MK4i. Perfect. So I'll insert him, and what I'm going to do is I'm just going to create a sketch on top of him, and just find out his just his dimensions. I just want to know like what its width and length is, what its height is, so that I can like do a rough sketch in my other CAD, in my other part studio. So I'll start a sketch on here, pairing sketch, normal to the plane, like this, and like this. I'm going to click I for coincidence, and dip. Bang, bang. Probably also want to know what this distance is. This is so I'm drawing all this so that when I make my you know, when I have everything attached in the assembly to the intake, I can tell whether it's going to hit something. And we can move stuff around. That's why we have CAD, because we want to know if there's going to be any collisions later. I'll just make them both 26 point. Yeah, I'll make them both 26. Could be rough. So got that. What did we say? Forgot. 207.167. Okay. 207.167. So I'm gonna draw a sketch on him. Bang. Just draw a quick triangle like that. Mirror line like we did before. Mirror. Oh, oops. Select the mirror line. Bang, bang, bang. Okay. And I forgot it already. 27.167. 27.167. And make those two equal. Oh wait. God damn it. That was not the correct thing to do because I wanted to have this guy a little bit off the line. Like there, right? Same with this one. So I'm just going to delete those constraints. Get that one there. Oh, that's not what I wanted to delete at all. Not what I want. Okay, I'll just do this. Something like that, right? Make these two guys equal if I haven't already. I'm gonna make this parallel to that, and this parallel to that. And we said that was gonna be, this distance is 26. and this distance is 26. Is that right? I might. Yeah, whatever. Okay. Actually, I'll make it 25, so it combines with the rest of the dry base. Otherwise, it'd be like floating. Should be a bit annoying. Yep. And then I want to know the height of it. Oops. The height of it is that. So why do I keep doing that? So I'll extrude him up by that height. Now we have something that kind of represents the Swerve modules, so that's good. Okay, now we probably want to do is the bumpers. So I'll I'll sketch this face, I guess, and I'm going to click U to use it to project the sketch, and I'm going to bring this guy up. This represents my bumpers, if you guys remember from the master sketch. I don't want to do that. I'll just draw a new line. Perfect. So then I can extrude this guy out all the way up to next. No, not up to next, up to face. I can click on this face. I'm gonna make a new one. Yeah, blue bumpers, nice, looks good. Sick. What's next? I probably want to do the holes. So in order to do the holes, the holes that are on the dry base rails that you can mount things to. Do that. They are always 12.5 mil away from any edge. There's a gap in the Swerve module, right? There's not going to be any holes here in the corner. So I did write down somewhere where that gap, how much that gap actually is. Right, so I've written down that it's going to be 119.8. Don't ask me how I got that number, I don't remember. And you won't have to do this because you'll have the actual CAD, your real thing, right? Linear pattern. 3 of them. Linear pattern means that you can it's just a linear pattern. I don't know how to explain linear pattern. Dang it. Linear pattern. Sorry, I'm going a bit quick because it's not this part isn't so relevant to the intake, and I want to keep the video relatively short. But create multiple instances of sketch entities uniformly in 1 or 2 linear directions. Cool. That's exactly what we want, because we want kind of like a grid of holes. We said 12.5 spacing. And I'm going to make 3 rows. Sorry, Andrew. I'm about to do 20 of them. Is that enough? Let's go for 24. Yeah, that's probably enough. And I'm going to remove everything in that sketch. I can click on the sketch to just select all of the faces, all of the closed contours in that sketch. And I'll do through all, so that it goes all the way through the other side. Sick. So now we've got kind of like our drive base frame done up with all the holes. Kind of represents what our real drive base is almost going to look like. A very rough version of it at least. Okay, so now that I've done that, what I'm going to do is hide the sketch that's visible, because I don't want to see that, and I'm also going to put anything related to the dry base into a folder. So anything up until looks like sketch 2, right? So this to this. I just held down shift to select them all. But I can do dry base rough. You can click add sketch to folder and you can add them to a folder like that. Sick. So now it's much more clean here for things that I probably won't ever touch again. Awesome. So now what I will do is start the sketch of the pivot plate, the plate that drives my gearbox, right? I mean my pivot, the gearbox that drives my pivot. So I started a sketch on this face because it's going to be directly mounted to that box tube, and I'm going to click N to go normal, right? Okay, so like we did with the intake, we need to figure out where all of our holes need to be before we sketch the perimeter of this shape, of this gearbox plate. So what that means is the first thing that we need to do is find out what the ratio of our pivot is going to be, of our gearbox is going to be, that will drive this pivot. So the way we do that is we go into recalc. We love recalc, and recalc has an arm calculator. So we'll go to here. Okay, so what we'll be doing is we'll be driving it with one neo vortex. Typically all you need. The ratio we don't know just yet, so I'm going to leave this for now. The efficiency, well, the more gears and pulleys and chains that you have, the less your efficiency goes down, because you can imagine there's no energy transfer that's actually 100% efficient. This is not realistic. So I'm going to put this at 90, just to compensate for any energy loss, such as energy loss to friction, to sound in our gears, in our chain, that kind of stuff. Our current limit, I think we can up that a bit to 60 amps. We can talk about how do you decide on a current limit in a future day. I'm not going to get into that now. My center of mass distance. So in order to figure out, whether the motor can drive this arm, you need to know how heavy the arm is going to be and where that mass is like centrally located, right? So the first thing I'm going to do is I'm going to go to metric kilogram, and I'm probably just going to want to calculate the distance between these two holes. What do you mean? That's kind of annoying. Okay, the center distance is 333. Now that's not actually going to be the real center distance, because what I really am looking for is like, where is the center of mass of the whole intake? If you think about all the wheels and the pulleys and all that, it's probably going to be somewhere around here. We can only actually know once we've assembled this guy, but we could even there's functions in CAD that you kind of check around where the center of mass is going to be. It's not 100% accurate because there is other stuff that you add on, but it's pretty good for a rough sense. But regardless, because the motor is back here, it's going to pull it back a bit. I'm gonna just put the center of mass there for now, and no, that's not quite what I want. But I can just click on these maybe. Min distance, that's not really what I want. I want the center distance, 227, right? 228 actually. My arm mass, I don't know. Again, you can kind of figure this out in CAD. Give you a rough value, but I'm just going to go for 3 kilos. Now that I've got that, I need to know, how much I'm swinging. So that's what we made our master sketch for. We found this dimension, which is 85.831. So we'll put this guy in. Okay, 85.831, and that's cool. And now I'm just gonna bring this guy down, and as you can see, as you bring it down, the speed goes up. So I'm gonna try 50. Speed's at 0.18. Oh, and at some point, you can see at some point you reach you bottom out. You reach kind of like a minimum time. That's probably what we want, right? If we go look at our graph, we'll be pulling 60 amps for about 0.08 seconds, and then it'll have reached is it reaching max speed, or is it just, okay, don't worry about it. Regardless, we're going to go for a 40 to 1 reduction. That seems good. I'm going to delete that point. So with a 41 reduction, we should get the intake coming in and out in 0.13 seconds. I think that's fast enough. Should be fast enough. If it's not, we can have a look at it once we've built it, right? But let's talk about how we're going to get that reduction. We can do that with, so right now we're using chain to drive that pulley, that pivot. I think I mentioned that in last video, and the reason that we use chain is because it's very good at shock loading, in the sense that this intake is sitting outside of the robot. It can hit the field wall, it can hit other robots, it can hit, there's a truss that's always somewhere on the field, and if it hits that, it's going to send a shock. It's going to try push it, move up the intake, put it back into the robot, which could be fine, but if your motor is applying a torque to keep it in that position, that's going to push against, the motor is going to push against, the intake hitting into the wall. And because of that, you could end up, for example, if you have a gear driving that pivot, you could end up shearing that gear tooth. The gear tooth could break, which is why we use chain, because it's good for shock loads. We can also use belt, right? Belt would also work, but belt has a lower tensile load capacity. It's harder to tension, so we might have more backlash with belt, and it also could skip, whereas chain, there's no real chance of it skipping if it's tension right. So we're going to use chain for the last stage of our gearbox. Now, how do we calculate the rest? Well, what we can do is just come up with an Excel spreadsheet and say, okay, my last stage, I think we had a 36 tooth on our sprocket, our pivot sprocket. Sorry, let's do stage 1, 2, 3 of our gearbox. Input, output, kind of bigger, smaller, right? So our pivot had a 36 tooth sprocket. Let's have a look at what other options we have for sprockets. 25. We're probably going to have it on a 1/2 inch hex, and let's do a single hub. 18 tooth. Let's do that one. So 18 ratio equals this divided by this, right? My input. So let's use a max planetary as the input. That's just a planetary gearbox, all packaged up nicely for us. They're really nice to use. I would avoid it if you're looking at some very low backlash solutions, because there's no way you can adjust the backlash inside of this gear cartridge, right? Whereas with a gear that you put on a shaft, you can do multiple things. You can seal it up. You can put retaining compound on it, which is almost like a glue to fill up holes, which should get rid of backlash. You can also put a steel shim in it to shim the shaft between the gear, and that kind of gets rid of the gap, because all our gears are designed to just slide onto shafts. They're not tolerant to be pressed on. They can still move around the shaft, and that brings in backlash. So by putting in the retaining compound or putting in the shim, you remove that backlash, but you can't do that with a gearbox like this. So if you have any if you want to make an arm that needs to have really zero backlash, because you need to go to multiple positions, I would try to avoid using this, but otherwise it's quite good. So with that, we've got these options for the ratios for the cartridges, right? So ratio here is this divided by that. So the total ratio is going to be this times this times this, right? So right now we have a 10, and we want it a 40, so we kind of need a 10 to 1, 4 to 1, sorry. So let's say I'm going to use, I'll show you here. Okay. We need a small gear, we need a big gear. I wouldn't use anything under 22, maybe, wait, that was 3/8. I wouldn't use anything under 22 because this has a high likelihood of shearing. We've had them shear in the past, just from like normal use. Let's go for 22. You know, if it does, the smaller the gear, the more likely it might shear. If it does shear, you could like add an extra gear. So you kind of have like double the surface area, or you could go to a bigger gear, or you could go to like a steel gear, which I don't think they sell. Oh wait, they do. You could go to a steel gear, but it is more heavy, which is why we tend not to use them, right? Yeah, like this one here. If you did go steel, you could probably even go for like a smaller gear because it's a lot stronger than aluminium. Aluminium is just light, which is why we like to use it. So we have 20, and then in order to have a 4:1 there, we probably want, that's an 80 tooth. Don't like it. It's a bit big. So what I'll do, go back here. We could go for a 9:1, right? Now we have an 18. This divided by this. So yeah, it's too much, but we can go to like 50 maybe. Too much. 48, 46, 44. Yeah, that's pretty close to what we want. I'm happy with that. If we put that into recalc, 39.6. Great. So I'm going to copy that and I'm going to pop that in here, just for future reference if I ever need to look at it. So that's good. Now we can start to draw up all the holes. Okay. So first thing we probably want to do is, you know, project the holes that we know are going to show up in this plate into our existing sketch. So that hole isn't really going to show up, but there is, you know, we have a bolt that's going to go into here, so we can use that. And I'm going to make that a construction line. Yeah, and I'll put a hole here. That's, well, let's make that an 8mm bolt, 8.1. Sorry, because it's clearance. It's going to be a bolt that goes into a hex shaft, and that hex shaft is going to spin in a bearing. Because the sprockets, they have a bearing size hole. You'll see later. Yeah, and then what we want is something that represents the 18 tooth sprocket. So this guy over here. Now, like we did before, we can go back into, I'll go to this one. We can go back into the sprocket drawings and figure out what the diameter of the sprocket is going to be with the chain, and we can draw that up just so that we kind of have a reference diameter that we can avoid. Yeah, good enough. I just want the reference diameter. So an 18 tooth has that reference diameter in inches. Yep, so that's cool. It's going to sit like here, and then we need a bearing bore because that sprocket has a hex hole, so we need kind of like a hex bearing in our plate. It's actually going to be a hole, so we're not going to make that a construction line like we did the other ones. Yep, this distance here is going to be defined by the number of chain links that we need. The way that you do that actually is you kind of like position this guy around where you want him. So let's say there, and dimension it like that, right? Now what we can do is we can go into recalc, chain calculator, chain type 25, my desired center in millimeters, it looks like 188.077. I've got an 18 tooth to a 36, So it's suggesting either I can use 86 chain links or I can use 88 chain links. I'm gonna go with, if I come closer, I'm getting pretty close to the Swerve drive, and I kind of want to avoid it. So I'm gonna go to 192.8175, just to clear the Swerve a little bit more. And then I guess, yeah, you could draw like the chain. We'll see whether we need it later. I'm not so sure. Actually, I'll draw it. Why not? Just as a reference, in case something is, we might be able to catch something colliding with the chain in the sketch and fix it up. So I'll make this tangent. And coincidence. Okay. Now that I've done that, I can draw where the gear is going to go. So I've got a big gear here. Remember, we have the 44 tooth. So that goes the 44 tooth. Next, there is a formula for knowing like the outer diameter of the gear, because we're going to use this as a reference again, so that we know when we draw stuff, it's not going to collide with the gear. But if you don't remember the formula, you can always go into here. What did we say? It was 44. And then in here, a 44 tooth gear has a 2.3 inch outer diameter, right? Yeah, so the formula for that is 44 tooth divided by 20 plus 0.1. Oh, all in inches, sorry. No equal sign. Inch. Keep in mind we are using like the 20 dp gear. This guy. 20 dp. That just defines like how big the teeth are, but pretty much all of our gears are 20 dp. So that's that. Right. Is that right? Yep. Cool. And then the other gear is 20 tooth. So I'm going to do the same thing. 20 divided by 20 inches plus 0.1 inch. That's just the outer diameter, right, of the two gears. I can set their distance using this formula. It's the sum of the gears in inches divided by 2 times 20 inches plus 0.001 for clearance. Oh, what is it angry about? Cannot add area and a length. What? Okay, like that. So those gears are going to mesh now at that center distance. I'll probably want a bearing there as well. 5 inches. Yeah. Okay. Then what I will do is set the what can I do? I guess I can like set the height of this so that it won't hit the box tube. 30, I guess. What are you mad about? Oh, right, and I can set the position of this guy. I'll just make these two vertical with V. This guy. So now they're in line vertically. What I would never recommend doing here is constraining like this to a specific hole, because if we were to move stuff around and it's constrained to a specific hole, that's gonna mess with stuff. You know, if we're constrained like horizontally to like that, I guess that would be a good example. Is, you know, it's now constrained 142 mil from that hole. But if, like, in our master sketch, if we move something around and pushed it back, it's still going to be constrained 142 mil to that hole. So it doesn't really make it compatible to edit later. So I would only really constrain to, like, the top face of this. Yeah. So now I think what I will do is I will draw the holes for the max planetary. Yeah. So max planetary, he looks like this. We can mount with these 4 holes. We just need to figure out where they are. How do we figure out where they are? We can go to the output hex socket drawing. Perfect. So they are no, not good. Let's go to the system drawing. Ah, perfect. There's 4 1032 holes, which are those guys, and they are 45 degrees offset. So what I'll do, maybe there's a better way to do this actually, I'm not so sure, but I'll do it this way. They're on a 2-inch belt circle, as expressed by this drawing, this dimension right here. So put that on 2-inch belt circle, construction line. Love our construction lines. And I'm gonna do, 1032, we said that's the equivalent of like M5, but this is gonna be an axis hole for the bolt head. So I'm not gonna, what was I saying? I'm not gonna make it 1032. I want to make it bigger. I'm gonna make it big enough for, like, maybe even a bolt, but an Allen key at least, right? And draw a line to there and a line to there. They can be construction lines, but they are definitely going to be 45 mil apart. Then I can do. I'll just mirror them. Right, put a line like that, why not? Mirror line, like that. So now I've kind of like, oh, that was a bad idea. Don't do that mirror line, because that's only correct in like a single position. Instead, what I will do is a circular pattern. And I'm going to click on those 2 holes, and I'm going to move my pivot point here. My number of instances are going to be 2, and now I've got that right. And now this will spin around, and they're all correct. I can mount this motor in any way, in any of these orientations. But there's only one real correct orientation, that's this one here. Why do you ask? Because if I was to put it here, you can see we draw gear before, right? And now if the bolts are here, those axis holes are doing nothing. The Allen key, when you put it through the hole, it's just going to hit the gear. So I want it to clear the gear. I want it to clear, yeah. So I'm going to put it here. It's blue, which I don't like, so I'm going to draw a horizontal line. Actually, instead of that, I'm just going to make these 2 holes, these 2 points horizontal. So you click H, bang, bang. Nice. Sick. The next thing I'll do is I will pick out where these standoffs are going to sit. There's going to be a plate behind this that holds the gearbox. I guess I didn't actually state that explicitly, sorry about that. But pretty much it's going to be a plate behind this that holds the gearbox. And we need to support it somehow. It's going to be mounted to this dry base rail, but we need to support it in other ways if we can. So, it's going to be a hole for it. Actually, I'll leave that for now. That's going to sit there, for example. It's going to be an M5 hole. And it's going to sit on a spacer. A spacer is going to space them out. Construction line. And that spacer is going to be 10 mil diameter. It's going to sit like this. now we need to like actually determine the position of it. So that spacer, I guess we don't want it to hit the gear, this gear here. So I'm gonna put it 4 mil away. And we also needed to like clear the gearbox, and you know, like I could try to figure out where everything on the gearbox is and do this in the sketch, but honestly I'm too lazy for that. So I'm gonna make this 8 mil now, and then when I put it all in the assembly I can actually check, is this gonna hit? That's why we CAD, as we said before. I'm gonna do 2 spaces, so I'm just gonna put a vertical line here and mirror that spacer over, just like that. So you can see, that's why we drew the train actually. Spacer is hitting chain. Not good, right? Oops. Not good, not good. Let's increase this guy. Perfect. Now the chain will clear spacer. Everyone's happy. And yeah. Is there anything else that I want to draw? I'm gonna pick up these holes. Why do I pick up all of these holes, you may ask? It's because if I was to select a few holes that like aligned with my current state of my plate, it would result in, it would be fine, except if I was to go and move, you know, the position of this, my CAD will go all red, because it's like, it thinks, for example, that I'm only using these holes that I've drawn in my perimeter here. But then if I move these circles to be like out here, they're really very far apart, right? So what I'll do is I'll only actually decide which holes I'm going to use after I've fully done the CAD. And I'm happy with the positioning of everything, just to make my life easier in the future if I need to make adjustments. So now that I've done that, I suppose I can start to draw out the perimeter. So like we did before, we get our friendly center point arc, and we just start drawing arcs around stuff that we want to make the perimeter. Bang, 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 just like that. Yeah. You know, you could do it on these holes, but like I said, I don't really want to pick a hole right now. It's not a good idea. So now I will start to draw the perimeter. So that one connects to there. That one, just making sure I don't do those like magnet constraints. Can get annoying later. It's not what you wanted. I'll do them manually if I want to in the future. This magnet constraint is fine because I do want this line to be parallel up to here. The reason I didn't make it coincident with this line, these 2 lines collinear, is because I just want to save weight. I don't see a point in this being that thick. There's no point. I'll put it up here. Up here, I'm actually going to make my perimeter a bit weird. I'm going to make it like this, and we'll see why in the very near future. It's a surprise. Then I want to fix up my perimeter, right? So I'm just going to make everything tangent. Click T. Bang, bang. Is that everything? Yep. Sick. Okay. I'm probably gonna tell it this is gonna be like 4 mil away. It's fine to dimension to a specific circle, because this one of these, because it's just a distance away. Like if it was to move to the side, it would still be 4 mil vertical away. That's absolutely fine. Yeah. What's going on here? So I'm just trying to see what's allowed to like move in this CAD, right? Oh, of course. So this isn't actually dimension, this distance. This is like the thickness of the edge of the plate away from ooh. Oh god. So that was bad. Let's start again. Draw that. Okay, That was not fun, right? I'm gonna delete this, and I'm gonna do that all again. This is gonna be 8 mil. This is the distance, the thickness between the bearing board and the edge of the plate. This will come out to here. And I'll do tangent again. Those two on tangent. Okay, same kind of deal. Actually, what I'll do here is I'll make this and this tangent. Yep. Then I just want to finish it up, so I don't know. This can be. Oops. That was supposed to be a distance. This can be 6 mil away. Just whatever looks good later. Can modify that if I want to. That. I get the. Yep. Make that 100. Sure. And I guess I can also make this one 100. These are just random numbers. Like I said in the last video, I always want these to be like numbers that mean something, but right now I just can't think of anything. Make this 130. I don't know. What else does it need? I guess I can like. Oh, I don't want that. I don't want that. It constrained that dot to the line. 45. Yeah. Sick. So now I can extrude that out. That and that. It's going to be a 6 mil plate. Perfect. Quick pause. I just want to check how far in I am. 50 minutes. Ouch. Okay. Okay. So now, what I'm gonna do is draw the plate that mounts the max planetary, right? So, in order to do that, I'm gonna start a sketch on this face, and I'm gonna pick up the holes that I need. So I definitely need this hole. I need the positions of the max planetary bolts and spaces to the plate. These are going to be construction lines. Q. Yeah, I think that's about it. Oh wait, I need this one here, which is also, you know, this is going to be a hex that runs all the way across, and I'm just going to use this as a bearing to support it. Yeah, so now that I've done that, I can start the sketch around that. So, like we've done so many times now, that, just sketch the arcs around the parameters, right? Bang, bang. Okay. Oops. It's not what I wanted. Don't even know how I pressed that. Draw the perimeter. Wait. I said before I don't want it to touch the bottom of the rail. Something like that. And make those tangent. So I make these two arcs equal. Give us a little symmetry in our lives. It's not quite what I meant. Oops. Let's dimension this to be, so I'll just dimension this to be 10 mil. No, sorry. I want to make this the size of this arc. Oh, what is going on? It's not what I wanted at all. Let's just delete this for now. make this equal to that. Yeah, makes sense, I guess. I was doing that. Oh god, what are you doing? Hey, that's not what I said. Is that what I said? Sorry, let's start again. Oh, right. See how I can't press on this line here? It's kind of hard to. You can press on this button, and you can press on all of them. Oh god. Okay, this is way too weird. Okay, sorry about that. Let's do that again. Use construction. No, not a construction line. Center point arc from there to there, and make it equal to that guy. Yeah, that's what I want. Make those two equal. Just gonna delete that and do that again. And center point arc here. Make it equal to that. And then I can just do this. Tangent, 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 tangent. What else I need? No. Okay, same thing, formula way. Then what do you want? I don't know, I guess I could like make this, use that by making it coincident, these two lines. Make it kind of like symmetrical as well. Q, and then I can go symmetric, shift Q, and mirror line, bang, bang. That should make them symmetric, right? Oh wait, I forgot to remember that these holes here need to be holes, mounting holes for the gearbox. So those need to be 1032, so 5.1. Just like that. So yeah, those are, you know, our unpocketed gearbox plates. Don't worry about the holes for now. These holes here, we'll fix that up later, as well as the shape. We might want to like widen this guy out a bit. I'm just trying to finish the video a bit earlier because it is quite long. But yeah, thanks for watching. We'll get right back into it next video.